Okay, so we'll go ahead and get started. Again, exams I'll have Monday at the latest. I'll try my best to get them back tomorrow, but Monday I'll be able to get them back for sure. Okay. So what we're going to do in this section, this chapter, chapter 4, and this is going to be the last chapter on derivatives or involving derivatives, is essentially just we're going to use first and second derivatives to help us describe graphs of functions. Okay, so today we're going to focus on learning how to find where functions are increasing, figure out where they're decreasing, and then also find what are called the local max and mins. Okay. The next chapter we're going to talk about second derivatives, and they tell us where the graph either curls up or curls down. It's called concavity. And then once we have that, where are we going after that? Then what we're going to do is we're going to do optimization problems. So we'll be back to doing some business and economics applications. Like we'll be trying to maximize profit, maximize revenue. Of course, you want to minimize your costs. So you'll try to figure out how many units do we have to sell to get maximum profit, maximum revenue, or minimum cost. And then once we're done with chapter 4, we're going to start talking about integration, which is really going backwards. So instead of taking a function and finding its derivative, you start with a function and you find another function whose derivative gives you the one you started with. So integration is kind of like doing derivatives backwards. Okay, it's like so you start with a function. What's a function whose derivative gives me what I started with? Okay, and then our main application in the integration chapter, I think I already mentioned it already. It was talking about the future value of a continuous income stream. In your economics classes, or even in section 3.2, we talked about how to find the future value. Well, you might have done it in pre-calc too, right? Where you just make one single investment, you can talk about what the value of that investment is in the future. But what we're going to do is we're going to tack on an extra piece. Rather than just doing one single investment, is I might, as a business, I might have some money flowing in, and every instant that I'm taking in money, we call it a continuous income stream, we turn around and immediately invest it. So it's continually receiving money and turning around and continually investing. And then we'll talk about how to find the future value of all those continuous investments. Okay, so that's where we're going. So we'll talk about first derivatives and graphs here. So this is 4.1. First derivatives and graphs. Okay. And I'll start by talking about increasing and decreasing functions. And sorry, on the first page in this first example, I didn't leave you enough room. So in the future, I'll have to make sure I fix my handout. But so one thing I'm going to do first, though, before I tell you these facts that are in the boxes. Yeah, sorry, Jordan, those handouts are there. I'm just going to draw a graph. This is some function, f of x. Okay. And we can just, by looking at the graph, if you have the graph already, you can find the parts of the graph where the function is increasing. So over on the left, the function would be increasing to this point, and then from there it starts decreasing again. And then the other place where it would be increasing would be down here at this minimum. Okay, and then it would increase as you go off to the right. Okay, now one thing you might notice is if you look at any point on the graph where you're increasing, and you look at the slope of the tangent line, that slope has to be a positive number. Okay, same thing over here, right? If I look at point on the graph and I think about the slope of the tangent line there, it's going to be positive. And then what do you notice about parts where the graph is decreasing? So mainly right here, if we look at the slope of the tangent line right there, okay, anywhere where the graph is decreasing, the slope of the tangent line would be negative. Okay, so what this is really telling me, and we know that derivatives give us slopes of tangent lines. So anywhere where the derivative is positive, i.e. the slope of the tangent line is positive, the function is increasing. Anywhere where the derivative or the slopes of the tangent lines is negative, the function is decreasing. So that's that first little box on your paper.
if f prime of x is greater than 0 on an interval I, then f is increasing on that interval. This marker is probably not going to show up very good in the video, is it?
Oh, that's awful.
So sorry, give me a minute. So f prime of x, if the derivative is greater than 0 on an interval I, then f is increasing on that interval. And then second, if f prime of x is less than 0 on an interval, then f is decreasing on that interval. Okay.
So you can think about this in terms of like cost, revenue, profit, right? Like you take the derivative of your cost function, it's negative on an interval. That just means for those levels of production, your cost would be decreasing if the derivative was negative, right? If you have like an interval that represents a range of production where the derivative of cost would be positive, then you know the cost would be increasing for those production levels. And then give me a second here. I gotta see if I can find a good marker.
That one's okay.
We'll see how these ones work. Okay, so that's what that first box is. Okay, right? In the first part of the box, it tells you the sign of the derivative. If it's positive, f of x is increasing, meaning the graph is rising. And then there's 3 examples of how a graph can rise. Right? So in this case here,
Your graph could curl upward, it could curl this way, or maybe it's just a straight line. Okay. And then in the case the function is decreasing, it can curl downward, curl upward, curl downward, or just be a straight line decrease. And then these shapes are going to be determined by the second derivative. We'll talk about that in the next section. If you're curling upward, we call that concave up. If you're curling downward, that's concave down. But we need the second derivative to know about that shape. So the first derivative is just going to tell us about increasing and decreasing. The second derivative is going to tell us more about the shape, whether the graph's curling up or curling down. Okay? So those are 3 possibilities for increase and decrease. So what we're going to do in this first example, one thing I also want to point out to everybody before I move on, is if you look at these places, right, this is a point where your function changes from increasing to decreasing. And what's the slope of the tangent line going to be at a point like that? It'll be a horizontal tangent line, so the derivative would be 0. Same thing over here. Anywhere you change from decreasing to increasing, you'll also notice you have horizontal tangent lines. Okay, so there's something special about places where you have a horizontal tangent line. Okay, one is it tells us where the function changes from increasing to decreasing or vice versa. The other thing it does is it kind of tells you where your what we call local minimums and local maximums are. Okay, and they also help you find the global or absolute maximums. Okay, so. And we'll talk about that when we move on. Right now, we just want to talk about increasing and decreasing. Okay. Everybody okay with the general idea? Okay. All right. So, example 1. Let me make sure I hit record. I did. Okay. So we're going to take a pretty simple function, f of x. It's going to be a quadratic. So 8x minus 2x squared. And then part A, which x values correspond to horizontal tangent lines. Right? And from the previous picture, those x values are going to tell me where the function changes from increasing to decreasing or vice versa. Okay. All right. And then in part B, well, let's do part A first. So I want to find x values that correspond to horizontal tangent lines. Okay, so first of all, what's the slope of a horizontal line? 0. And what's something that we can take that gives us slope of tangent lines? Derivatives. So if we want the horizontal tangent lines, we're just saying where is the derivative equal to 0. Okay, so what we're going to do is we're going to find f prime of x. Okay. Now, in this section, we don't really use that d over dx stuff as often. Okay, so almost exclusively we're going to just be using the prime notation. Okay. All right, so f prime of x, the derivative of 8x is 8, minus here the derivative of minus 2x squared is just, again, this is just a regular derivative. X is the independent variable, so we just have to use the power rule, and you'll get 8 minus 4x. So the 2 came out front, the power got reduced to positive 1. Okay. And then what we're going to do is set f prime of x equal to 0 and solve for x. And those will be the x values where the tangent line is horizontal. And again, on this first problem, sorry, I didn't really give you enough room. That's my bad. Hopefully there's enough room in the margins on the right side to kind of do what we need. Okay. So in this case now, we take 8 minus 4x, set it equal to 0. Now, do I really need to solve this, or can we just kind of guess what it's going to be? Yeah, right? This is not so bad of an equation. We could just maybe add the 4x to the right and divide by 4. But this is going to lead us to getting that x is equal to 2. That's the only place where the tangent line will be horizontal. Now, does that make sense? Right? If you have a quadratic, the place where the tangent line is horizontal is going to be at the vertex. Right? Because that's where the function will change from increasing to decreasing, or vice versa. Okay. All right. So now what we're going to do in part B is we're going to find the, does it say values of x or intervals?
Values of x.
Okay, so find the values of x, or for which values of x is f increasing or decreasing. Now, usually you're going to give, a lot of these functions are continuous. You can draw them without lifting your pencil. So the values of x for which a function is increasing or decreasing, they're always going to be intervals. Okay. And what we do for this, some of you might remember doing this in a pre-calc class, is when you solved inequalities, you made what was called a sign chart. Okay, we're going to do the same thing here. So what I'll do is I'll take a number line, and it turns out the only places where a function changes sign, or the derivative changes sign, is at these horizontal, the places where the horizontal tangent lines are. Right, I kind of erased the picture, but I can draw it again. Right, so I had this picture up here, something that kind of looked like this. Here's a place where the tangent line is horizontal. That also ended up being the place where the function changed from increasing to decreasing. So we just take a number line, we put the 2 there, and then we're going to test the sign of the derivative. Some of you might want to make a table, if you like, because now, what am I going to do here? Hold on. So you have an interval, a test value, and then you have the sign of f prime of x. So where that horizontal tangent line is going to split up the domain into 2 intervals. Okay, so you have the stuff left of 2, so minus infinity to 2. And then you have the stuff to the right of positive 2, which is 2 to infinity. You don't really need to make this table. If you're comfortable, you can just draw the number line if you like. And then what we're going to do is we're going to pick an x value in each of these intervals. So maybe on this one we can use x equals 0. That's an easy number. That's in that interval. Maybe this one we'll use x equals 3. And then we'll note the sign of the derivative. Okay. So what happens when I plug 0 into the derivative here? You get 8 minus 4 times 0. So at 0, the derivative equals 8. The sign of the derivative would be positive. Okay. And then what happens when you plug in 3? Yeah, 8 minus 4 times 3, that's 8 minus 12. That gives you a negative number. And then, if you like, some people just put pluses up here. That indicates that over here, f prime of x is greater than 0. And over here, you can put a bunch of minuses. That tells us that the derivative is less than 0. So your derivative only changes signs at a place where the tangent line is horizontal, possibly. There's for different kinds of functions, there's other places the derivative can change sign, but this is just a simple quadratic. So the answer to the question in part B is we can say f is increasing on the interval minus infinity to 2 and is decreasing on the interval from 2 to infinity. Okay. So we found where the tangent line was horizontal. That's the place where the derivative changes sign.
Would it be f or f prime?
The derivative tells us if the original function is
okay.
increasing or decreasing. Yep. So if you look at that first table at the top of the handout, you'll notice that in the first box they have the sign of the derivative. If f prime of x is positive, that tells us the original function is increasing. Okay. So we're using the derivative to tell us basically where the graph is rising and where the graph is falling. So to the left of 2, the graph is going up. To the right of 2, the graph is going down. And then I can kind of sketch a graph. Our intuition tells me I know this is a quadratic. Okay. Where the tangent line is horizontal, that's actually where the vertex is going to be. That's going to be the highest or lowest point. Although, this is another thing that's going to come up later. How do I know if it's a highest or lowest point? Well, you're increasing to a maximum value once you get to 2, and then to the right of that, you're going to fall back down. Plus, you also know, maybe from pre-calculus, is if the coefficient on x squared is negative, the parabola opens downward. Okay, is that familiar? Mm-hmm. Okay. If you have a positive coefficient on x squared, the parabola would open up. So for part C, I think I said to sketch a graph. So here's what I'm going to do. I'm going to go 2 units to the right. I guess we'll go 1, 2, 3, 4 on the x-axis. Anybody know what you get if you plug 2 into the original function? 8 times 2 is 16, minus 2 times 4. Yeah, so you get 8. Okay. So I'm going to say just go by units of 2 here. So 2, 4, 6, 8. So at positive 2, the function has a value of positive 8. And then I'm not going to worry about what the roots are. I mean, I think it's going to pass through the origin because when you plug in 0, you get 0. So I think it's 0 at 0 and 4. But like I said, to the left of 2, it's increasing until you get to where you have a horizontal tangent line. And then to the right of positive 2, it decreases again. So I think that would be a rough sketch of the graph of f of x. Okay, so the first thing we did is we figured out where this horizontal tangent line was. And then we plugged something into the left of 2 into the derivative. Since the derivative was positive, I knew the graph was increasing. And then you plug something greater than 2 into the derivative, you got a negative, which means the function to the right of 2 is decreasing. Okay. All right. Is that okay? Anybody have any questions?
So for more complicated problems, is it okay if we plug it into Desmos?
To sketch the graph?
Yeah.
Well, you're not going to have Desmos on a test. So the graph doesn't necessarily have to look perfect. It just has to agree with the signs of the derivative. Okay. So on the test, you're just going to draw a rough sketch, and it doesn't have to be perfect.
Certainly on the homework, yeah, like you can use the technology to aid when you graph it. Okay. But you're still gonna by hand have to be able, like you won't even, without even looking at the graph, you'll have to be able to find intervals of increase and decrease. And eventually we'll get to some more complicated ones.
Yeah, this is.
Okay. So, there's other things that can happen. So it's not about where the derivative is 0 that tells you where the function changes from increasing to decreasing or vice versa. You might have a rational function that has vertical asymptotes. Those are also places where you might have a function changing from increasing to decreasing, right? So before I get to the next part, which is called critical numbers, I just want to maybe blabber on for just a minute. So some other things that can happen, is you might have a vertical asymptote. The function might be increasing to the left, but it might be decreasing to the right. Okay? And it turns out at a vertical asymptote, that's also a place where the derivative is undefined. Right? The original function's not even defined, so the derivative wouldn't be defined there either. Okay? So there's two possibilities for where a function can change from increasing to decreasing or vice versa. One is where tangent lines are horizontal. The other one is going to be where derivatives don't exist. Okay, those are other places where you might have your function changing from increasing to decreasing or vice versa. Okay, so first of all, one definition. There's one that I don't have on the page, so you might want to make a note of this, and I'll have to fix this handout later. So before I talk about what are called critical numbers, that definition at the bottom of the page, there's what are called partition numbers. The reason I forgot to put them in here is because typically other textbooks don't talk about partition numbers, but it's actually, I think, a good idea. So a number x where f prime of x equals 0 or is undefined is called a partition number. Okay. And a little slightly more restricted definition is what's called a critical number. So this is the one you guys have at the bottom of the page. It's almost the same definition. So let me see. Read that definition at the bottom of the page. What would maybe be the only difference between a critical number and a partition number? Pay attention to the wording. So a partition number is just a number x. But what does it say? What's the even further restriction in the definition of a critical number? In the domain. Okay. So partition numbers are numbers where the derivative is 0 or undefined. A critical number is just adding in the extra restriction that it has to be a number x in the domain. I can't stress how important that is. Okay, so it's a number x in the domain where the derivative is equal to 0 or undefined. Okay. Oh, I just saw example 4 has natural log in it, but that's okay, I'll make up a different function. Okay. So, what we're going to do first is we're going to find critical numbers. And then I'll tell you how critical numbers relate to finding where a function is increasing and decreasing. And also they help you find what are called the local maximum and minimum values. Okay. Alright, so example 2, we're just going to find critical numbers. Sometimes the critical numbers and the partition numbers are the same, right? Because if your domain is all real numbers, well, then partition numbers are no different than critical numbers. Okay, but sometimes you have a partition number that's on the edge of the domain.
It's not really in the domain, but it's a place where the derivative is 0 or undefined. Okay, so we're going to find the critical numbers of the function f of x equals 1/3 x cubed minus x plus 2/3. Now, I guess all I could have said here, I could have just told you that a critical number is a partition number that's in the domain. Okay, that's another way of defining critical number. Okay. Okay, so you want to find critical numbers, what you have to do is you have to take the derivative. The derivative of 1/3 x cubed is going to be, I believe, just x squared, because the 3 that comes out front multiplies with the 1/3 to give you 1. The derivative of minus x is minus 1, and the constant 2/3 has derivative 0. And we might as well factor this. This is what we call a difference of
Cubes.
or squares, yep. And it factors as x minus 1 times x plus 1. So that means f prime of x equals 0 or is undefined. Now, the derivative is a quadratic. That's defined everywhere. So the only critical numbers are where the derivative is 0. And that happens when x equals plus or minus 1. And those are both in the domain of the original function, because the domain's all real numbers. So those are your critical numbers. And in this case, those are the numbers where the derivative is 0, and they're in the domain. So those would be giving you where your horizontal tangent lines are. Okay. So those would be the cutoffs where the function changes from increasing to decreasing. Right? We could make our table or our number line, and we could find the intervals of increase and decrease. We're going to do that for the next problem, though. Okay. Is everybody okay so far? So a critical number is, again, it's just where the derivative is 0 or undefined. Usually the undefined part is when you look at the derivative and you want to avoid places where you're dividing by 0. That's where you get the where the derivative is undefined. If you have a rational function, you take its derivative and it's again a fraction. Setting the numerator equal to 0 tells you where gives you the critical numbers where the derivative is 0. Setting the bottom equal to 0 is where you get the critical numbers where f prime is undefined. So I think we'll see that in this next example. I'd rather come over here because the video doesn't pick up that right half very well. So example 3. So if f of x is equal to 1 plus x to the 1/3, we'll find critical numbers, intervals of which f is increasing, and the intervals for which f is decreasing. Okay. So to do this, you have to take a derivative. You get 1/3 times 1 plus x, and then you raise it to the
Negative 2/3.
next lowest power, negative 2/3, times the derivative of the inside, which would just be positive 1. And this is equal to 1 over 3 times 1 plus x to the 2/3. Now, this is where simplifying, remember when I said that there will be a point where simplifying your derivatives matters much more? Well, this is that point. Okay. So you're going to have to simplify derivatives and make sure everything has positive exponents. Okay, so let's see if we can find critical numbers. So what are they again? They have to be numbers in the domain of the original function that make the derivative 0 or undefined. Now, if you have a fraction and the top is a constant, can that fraction ever equal 0? What do you think? Right? So first of all, the bottom can never be 0, right? But if the bottom is anything other than 0, 1 divided by anything non-zero is never going to equal 0. So this does not equal 0 for all x. So no critical numbers where the derivative is 0. But is there anywhere that derivative is undefined?
Where the bottom equals 0?
Yeah, right? If the bottom was equal to 0, this derivative would not be defined. So you don't get any critical numbers coming from the derivative equaling 0 in this case. This time the critical numbers only come from when the denominator is 0. And what's the only thing I can plug in for x to make the bottom 0? The power and the 3 don't really matter. You can just look at the 1 plus x. What makes 1 plus x equal to 0? Negative 1. Okay. So f prime of x. Now, I guess we could set the bottom equal to 0 and solve, but again, the 3 and the power don't really play a role. If I want to make this 0, I just need what's in the parentheses to be 0, and that happens when x is equal to negative 1. So f prime of x is undefined when x equals negative 1. So that's a partition number. How do I know if it's a critical number? It also has to be in the domain of the original function. Are there any problems plugging anything you want into this? Right? You can take the cube root of anything you want. So can I plug negative 1 into the original function? Yeah. So that's undefined when x equals negative 1, which is in the domain of f. Okay, so the critical number, there's only one, is x equals negative 1. Okay. So this is a good time too, where you'll probably have to maybe think a little bit harder about domains. Okay. And I'm more than happy to help people if you need to meet with me and get a refresher on finding domains. All right, so that's one piece. So now what I need to do is find intervals of increase and decrease. Okay, so what can I do? I guess we can make the table if you like. Some of you might just like drawing the number line that I drew, and that's fine. Some of you might prefer making the table. I can go ahead and do both. So what we'll do is our critical number is going to split up the domain into two intervals. Okay. And then what we're going to do is on each interval we'll take a test value, we'll plug it into the derivative, and we'll note the sign of f prime of x. And there's two intervals I've created. So what would they be? Everything to the left of negative 1. So negative infinity to negative 1. And then the other interval we've created is minus 1 to infinity. Okay. I wonder if I can fix this glare a little bit. Didn't help all that much, but okay. So we'll take a test value. So over here I can maybe plug in negative 2 as something in this interval. Over here I could plug in, generally 0 is the easiest thing you can plug in. So I'll take a test value. Remember, the derivative can only change signs at the critical numbers, or the partition numbers. Okay. So the derivative can only change sign at a partition number. And then now what we'll do is we'll note the sign of the derivative. So I got to come back over here. So remember, we'll look at f prime of negative 2. This is 1 over 3 times 1 plus negative 2 to the 2/3. Okay. And I don't really care too much about the value, but one thing you're going to notice is if you have a 2/3 power, what you're really doing is squaring first and then taking a cube root. Okay. So this is going to have what for a sign? Is it going to be positive or negative? Okay, again, a 2/3 power, you really are squaring something first. If you square something, it's going to become positive, so the derivative here is going to be greater than 0. If you're not sure, you can always plug this into your calculator. So the sign of the derivative to the left of -1 is positive, although even if I plug in 0, you're going to get 1 over 3 times 1 plus 0 to the 2/3. That's again going to be positive. So this function is essentially doing what? It is always increasing, except for at one point. The critical value, that's where the derivative is undefined. You actually get a vertical tangent line there. Okay. So generally, if the derivative is undefined, there's a couple things that can happen. Either the original function has a vertical asymptote or a sharp point, or the other thing is, the other possibility of where a derivative doesn't exist is where you have vertical tangent lines. Okay. So here, the function is always increasing, so you can just say f is increasing on the interval -infinity to -1 and -1 to infinity. Okay. And like I said, at -1 itself, the function is defined, but the derivative isn't. I think this is going to be a case where you have a vertical tangent line. So let me maybe try and sketch you a rough sketch of what this graph looks like. And again, I got to get some folder markers here. Let's try this one. I probably just tried this one. Oh, that's a little better. Okay. So here's -1. When you plug -1 into the function, I think it's pretty easy to see it's 0. And then what this function looks like, hold on, I gotta think. Ah, yes. That's essentially what the graph is gonna look like. Okay. So you can see it's always increasing, it's always going up as you go from left to right. The reason the derivative isn't defined at -1 because you actually have a vertical tangent line at -1. Okay. Right? And vertical lines, they don't have slope, so that's why the derivative is undefined. Okay. So this function is always increasing. The only critical number was -1. And that was when the derivative was undefined, so we're getting that vertical tangent line there. Okay. So I gotta make something up for the next problem, because I kind of have an issue, don't I? I have a natural log in there, so you can just cross that off. I'm gonna make up another function. Is everybody okay if I get rid of this piece? Okay. So example 4, same thing as the previous question, critical numbers, intervals of increase and decrease. But how about I say f of x this time is x over x minus 2. We're going to find critical numbers. We'll find, and then we'll find where the function is increasing and decreasing. Now this function does have a vertical asymptote at x equals 2, because 2 makes the bottom 0, but it does not make the top 0. Okay. You might as well do this from now on too. It's a good habit to get in to just write down the domain of the function. So the domain would be everything but the number 2, because that's what would lead to division by 0. So the domain is -infinity to 2, union 2 to infinity.
Would we still take the derivative of that?
Yep. Yeah, anytime so basically it's calculus, right? Every problem comes down to a derivative in some way or form, way, shape, or form. And the way that you find intervals of increase and decrease is you take the derivative and you find the partition or critical numbers. Yeah.
Could we have written the answer over here, like with the U?
Yeah, I suppose. There's gonna be, yeah, I don't care if you write it with a union or just say and, that's fine. Yep. Okay. So like Ollie said, or was curious about, is we are gonna need a derivative because we have to find those, although this time when we're gonna find critical numbers, but you know that number line that I made? You actually use all the partition numbers as well. Okay, the critical numbers really are just, we're going to see where they come in later. If you have a place where the derivative changes sign, then add a critical, in the numbers a critical number. That tells you where you have the local max and mins. The partition numbers, right, 2 is not in the domain here. We're going to see that 2 is a place where the derivative is undefined. So that's a cutoff point where the function might change from increasing to decreasing. So first, let's go ahead and do this. We have to use the quotient rule. So it's going to be the bottom function, x minus 2, times the derivative of the top, which is 1, minus the top function times the derivative of the bottom, which is also 1. And then we divide by the bottom function squared. So low d high minus high d low over low squared. Okay. Then we can clean up the numerator a little bit. It becomes x minus 2 times 1 minus x over x minus 2 squared. The x's cancel, and you just get negative 2 over x minus 2 squared. So there's your derivative. Okay. Now, again, since the numerator is just a constant, will this ever equal 0? Okay, so the derivative will never equal 0. But f prime of x is undefined at what value? 2. At x equals 2. Which, I'll say this, is a partition number. But why is it not a critical number?
It's not in the domain.
Exactly, it's not in the domain of the original function. Okay, so it's a partition number, but it's not a critical number. So, but you're still going to use that. That's still going to split up the domain into 2 pieces. Sorry, the domain was already in 2 pieces. Okay, but that x equals 2 is your cutoff point. So now you can make your little chart or table. You can write down intervals. You can write down, sorry, I forgot to write this, which is a partition number. There's actually no critical numbers this time. So sorry, I forgot to write that piece. Okay. So you get a partition number, but not a critical number. We'll take a test value, and then we'll note the sign of f prime of x. So the 2 intervals that's broken up by the partition number is going to be negative infinity to 2 and 2 to infinity. So the partition number is to split up your domain. In this case, the domain was already split in 2 pieces, so the partition number didn't really do anything. And then what's a good test value? I think negative infinity to 2 has the number 0 in it. And then you can pick anything you want in the interval from 2 to infinity. Let's just plug 3 into the derivative. Okay, so here's my derivative. So notice the bottom is squared, right? You have a square in the denominator. So the denominator is always positive and the numerator is always negative. So is there really any point in plugging any test numbers in? The sign of the derivative is just going to be negative no matter what, because what's in the bottom is being squared. So what does that mean? It just means f is always increasing, or sorry, always decreasing. So I'll write f is decreasing on the interval minus infinity to 2 and 2 to infinity. Guess that one wasn't as insightful either. But we'll certainly do more. How much time do I have? I have 4 minutes. Let's maybe do one more. So this is an additional example. Tomorrow we'll talk about the local extrema and the first derivative test. We'll see if I have time. I'll start the next section, but I don't quite know if we'll get there. So give me a second. Let me pull up a function here. I'm going to go into my files from my other calc class. Let's try this one, see what happens. So example 5, we'll do one more of these. I don't really want to start a new topic. So example 5, let's say f of x equals x squared times the square root of x plus 1. So same question, you know, partition and critical numbers, and then we want intervals of increase and decrease. Okay, so first of all, if we're going to take a derivative, it would make more sense to write the square root of x plus 1 as x plus 1 to the 1/2 power. And now we have to use the product rule together with the general power rule. So f prime of x is going to be first function times the derivative of the second, and then technically times the derivative of the inside, which is just 1, plus the second function times the derivative of the first, which is 2x. I should have written this down right away too. The domain is -1 to infinity. Right? The -1's the smallest thing you could plug in underneath the square root. Right? Then you'll get square root of 0. Right? You couldn't plug in -2, for example, because you'd be taking the square root of a negative. Okay, so sorry, I had to go back and write down the domain here. And then now, this is a case where we have to simplify. Okay, so let's see all the stuff we can factor out. I think I can factor out, is there any powers of x that can come out?
Yeah.
So I've got an x squared and an x. You always factor out the lower power, so we'll pull an x out. Anything else I can factor out?
X plus 1 to the 1/2.
Now do I want,
There's -1/2.
yeah, so we have 2 powers of x plus 1. We're going to factor out the lower power. And then now we have to figure out all the stuff that's left over. So let's see, I still have the 1/2 there, and I still have an x. So all that's left over in the first term is 1/2 x. And then I factored out this x, you still have a 2. And I claim that you have an x plus 1 left over. How did I know I have a power of x plus 1? Well, because if I distribute the x plus 1 to the -1/2 back through and multiply it by this, you add these exponents together, -1/2 plus 1 would give me an x plus 1 to the 1/2. Okay, and then now when you simplify this, it's going to be x times 1/2 x plus 2x is going to be a 5/2 x